Module objectives. By the end of this module, you will be able to define total pressure and center of pressure. Explain how to calculate total pressure and center of pressure for vertical plane surface, horizontal plane surface, inclined plane surface, and curved surface, and define buoyancy and center of buoyancy. Forces acting on fluids at rest. Let's learn about the hydrostatic forces that act on fluids such as liquids and gases at rest. On the image, we can see the static fluid layers, which is nothing but fluid at rest. This means that there will be no relative motion between adjacent or neighboring fluid layers. The velocity gradient, which is equal to the change of velocity between two adjacent fluid layers divided by the distance between the layers, will be 0. Or in other words, du divided by dy is equal to 0. The shear stress, which is equal to tau, is equal to mu du divided by dy, will also be 0. Hence, the forces acting on the fluid particles will be due to the pressure of fluid normal to the surface and due to the gravity or self-weight of the fluid particles. Menu. This module has been divided into two sections: total pressure and center of pressure, and buoyancy and flotation. Click each section to explore more. What is total pressure and center of pressure? Let's learn about total pressure and center of pressure. The total pressure is defined as the force exerted by a static fluid on a surface, either plane or curved, when the fluid comes in contact with the surfaces. It always acts normal to the surface. The center of pressure is defined as the point of application of the total pressure on the surface. There are 4 cases of submerged surfaces on which the total pressure force and center of pressure is to be determined. The submerged surfaces may be vertical plane surface, horizontal plane surface, inclined plane surface, and curved surface. Next, we will learn about the submerged vertical plane surface. Submerged vertical plane surface. Consider a plain vertical surface of an arbitrary shape immersed in a liquid as shown in the image. Consider A is equal to the total area of the surface. H bar is equal to the distance of centroid position of the area from the free surface of liquid. G is equal to the center of gravity of the plane surface. P is equal to the center of pressure. H star is equal to the distance of center of pressure from the free surface of liquid. Consider a strip of thickness dH and width b at a depth of h from the free surface of liquid. Let's learn to calculate the total pressure and center of pressure of the submerged vertical plane surface. Click each term to learn more. Total pressure of submerged vertical plane surface. The total pressure, or F, on the surface is determined by dividing the entire surface into a number of small parallel strips. The force on small strip is then calculated, and the total pressure force on the whole area is calculated by integrating the force on small strip. Let's take a look at the equation for calculating the total pressure. The pressure intensity on the strip is P, which is equal to rho into G into H. The area of the strip is dA, which is equal to B into dH. The total pressure force on the strip is dF, which is equal to P multiplied by area of the strip. This in turn is equal to rho into G into H multiplied by B multiplied by dH. Therefore, the total pressure force on the whole surface is F, which is equal to integral dF, which is equal to integral of rho into G into H into B into dH, which is again equal to rho into G into integral of B into H into dH. However, integral of B into H into dH is equal to integral of H multiplied by dA. This is equal to the moment of surface area about the free surface of liquid. This in turn is equal to the area of surface multiplied by distance of the centroid position from the free surface, which is again equal to A multiplied by H bar. Therefore, F is equal to rho into G into A into H bar. For water, the value of rho or mass density is equal to 1000 kg per cubic meter and G is equal to 9.81 meter per second squared. The force will be in Newton. Center of pressure of submerged vertical plane surface. Let's learn about the center of pressure of submerged vertical plane surface. The center of pressure or H star is calculated by using the principle of moments, which states that the moment of the resultant force about an axis is equal to the sum of moments of the components about the same axis. The resultant force F is acting at P at a distance h star from free surface of the liquid. Hence, moment of the force F about free surface of the liquid is equal to F into h star. Let's consider this as equation 1. Let's take a look at the equation for calculating the center of pressure. The moment of force dF acting on a strip about free surface of liquid is equal to dF into h. Since dF is equal to rho into G into H into B into dH, this in turn is equal to rho into G into H into B into dH into H. The sum of moments of all such forces about the free surface of liquid is equal to integral of rho into G into H into B into dH into H, which is equal to rho G into integral of B into H into dH. This is equal to rho G into integral of B into H squared into dH, which is equal to rho G into integral of H squared dA. This is because B into dH is equal to dA. However, integral of H squared into dA is equal to integral of B into H squared into dH. This is equal to the moment of inertia of the surface about free surface of liquid, which is equal to I naught. Therefore, sum of moments about free surface is equal to rho G into I naught. Let's consider this as equation 2. If we equate equations 1 and 2, then we get F into H star is equal to rho G into I naught. However, F is equal to rho G into A into H bar. Therefore, rho into G into A into H bar into H star is equal to rho into G into I naught. Let's consider this as equation 3. Alternatively, we can also have H star is equal to rho into G into I naught the whole divided by rho into G into A into H bar, which is equal to I naught by A into H bar. By the theorem of parallel axis, we have I naught is equal to Ig plus A into h squared bar. In the equation, Ig is equal to the moment of inertia of area about an axis passing through the center of gravity of the area x dash x and parallel to the free surface of the liquid. Substituting the value of Ig in equation 3, we get h star is equal to Ig plus A into h squared bar the whole divided by A into h bar, which is equal to Ig by A into h bar the whole plus h bar. In the given equation, h bar is the distance of center of gravity of the area of the vertical surface from free surface of the liquid. Hence, from the equation it is clear that the center of pressure, which is h star, lies below the center of gravity of the vertical surface. In addition, the distance of center of pressure from free surface of liquid is independent of the density of the liquid. Let's take a look at the centroid position or CG and moment of inertia for different shapes. The first column in the table is plane surface. The second column in the table is CG from the base. The third column in the table is area. The fourth column in the table is moment of inertia about an axis passing through CG and parallel to base IG. The fifth column in the table is moment of inertia about base I. The first plane surface is the rectangular surface. For that, the CG from the base x is equal to d by 2. The area is b into d. The moment of inertia about an axis passing through CG and parallel to base IG is equal to b into d cube divided by 12. The moment of inertia about base I is equal to b into d cube divided by 3. The second plane surface is the triangular surface. For that, the CG from the base x is equal to h by 3. The area is b into h divided by 2. The moment of inertia about an axis passing through CG and parallel to base IG is equal to b into h cube divided by 36. The moment of inertia about base I is equal to b into h cube divided by 12. The third plane surface is the circular surface. For that, the CG from the base x is equal to d by 2. The area is pi d squared divided by 4. The moment of inertia about an axis passing through CG and parallel to base IG is equal to pi d4 divided by 64. The moment of inertia about base I is none. Submerged horizontal plane surface. Next, we will learn about the submerged horizontal plane surface. Consider a plane horizontal surface immersed in a static fluid. As every point of the surface is at the same depth from the free surface of the liquid, the pressure intensity will be equal on the entire surface and will be equal to P is equal to rho into G into H, where H is the depth of the surface. Consider A is the total area of the surface. Then the total force F on the surface is equal to P into area, which is equal to rho into G into H into A, which in turn is equal to rho into G into A into H bar. In this equation, H bar is equal to the depth of CG from the free surface of the liquid, which is also equal to H. In addition, H star is equal to the depth of center of pressure from free surface, which is also equal to H. Here, H bar is equal to H star. Submerged inclined plane surface. Next, we will learn about the inclined plane surface submerged in liquid. Consider a plane surface of arbitrary shape immersed in a liquid in such a way that the plane of the surface makes an angle theta with the free surface of the liquid as shown in the image. Let's learn to calculate the total pressure and center of pressure of the submerged inclined plane surface. Click each pressure to learn more. Total pressure of submerged inclined plane surface. Let's learn to calculate the total pressure of submerged inclined plane surface. On the image, A is the total area of the inclined surface. H bar is the depth of CG of the inclined area from the free surface. H star is the distance of center of pressure from the free surface of the liquid. Theta is the angle made by the plane of the surface with the free liquid surface. Let the plane of the surface, if produced, meet the free liquid surface at O. Then O' is the axis perpendicular to the plane of the surface. Y bar is equal to the distance of the CG of the inclined surface from O'. Y star is equal to the distance of the center of pressure from O'. Consider a small strip of area dA at a depth h from the free surface and at a distance y from the axis O' as shown in the image. The pressure intensity on the strip P is equal to rho into G into H. Therefore, the pressure force dF on the strip is equal to P into area of strip, which is equal to rho into G into H into dA. The total pressure force on the whole area F is equal to integral of dF, which is equal to integral of rho into G into H into dA. However, from the image, we have the equation as H by Y is equal to H bar by Y bar, which is equal to H star by Y star, which in turn is equal to sine theta. Then H is equal to Y into sine theta. Then F is equal to integral of rho into G into Y into sine theta into dA, which is equal to rho into G into sine theta into integral of Y into dA. But integral of Y into dA is equal to A into Y bar, where Y bar is equal to the distance of CG from the axis O'. F is equal to rho into G into sine theta into Y bar into A. This in turn is equal to rho G into A into H bar. Since H bar is equal to Y bar sine theta, center of pressure of submerged inclined plane surface. Let's learn to calculate the total pressure of submerged inclined plane surface. The pressure force on the strip dF is equal to rho into G into H into dA. This is equal to rho into G into Y into sine theta into dA. The moment of the force dF about axis O' is equal to dF into Y, which is equal to rho into G into Y into sine theta into dA into Y, which is equal to rho into G into sine theta into Y squared into dA. The sum of moments of all such forces about O' is equal to integral of rho into G into sine theta into Y squared into dA, which is equal to rho into g into sine theta into integral of y squared into dA. However, integral of y squared into dA is equal to the moment of inertia of the surface about O dash O, which is equal to I naught. Therefore, the sum of moments of all forces about O dash O is equal to rho into g into sine theta into I naught. The moment of the total force F about O dash O is equal to F into y star. Here, y star is equal to the distance of center of pressure from O dash O. Equating the two values, we have F into y star is equal to rho g into sine theta into I naught. Alternatively, y star is equal to rho into g into sine theta into I naught the whole divided by F. Equation 1. Now, y star is equal to h star divided by sine theta and F, which is equal to rho into g into a into h bar. By the theorem of parallel axis, the value of I naught is equal to Ig plus a y bar squared. Let's substitute these values in the equation 1 for y star. We then have h star by sine theta is equal to rho into g into sine theta the whole divided by rho into g into a into h bar the whole multiplied by Ig plus a into y bar squared. Therefore, h star is equal to sine squared theta divided by a into h bar the whole multiplied by the Ig plus a into y bar squared. However, h bar by y bar is equal to sine theta or y bar is equal to h bar by sine theta. Therefore, h star is equal to sine squared theta divided by a into h bar multiplied by the whole of Ig plus a into h bar squared by sine squared theta. Alternatively, h star is equal to Ig into sine squared theta divided by a into h bar plus h bar. If theta is equal to 90 degrees, then the equation for inclined surface becomes equal to the equation for vertically plane submerged surfaces. In the last equation, Ig is equal to the moment of inertia of the inclined surface about an axis passing through G and parallel to O dash O. Submerged curved surface. Let's learn about the curved surface submerged in liquid. Consider a curved surface AB submerged in a static fluid as shown in the image. dA is the area of a small strip at a depth of h from the water surface. Then the pressure intensity on the area dA is equal to rho into g into h. The pressure force dF is equal to P into area of the small strip, which is equal to rho into g into h into dA. This force dF acts normal to the surface. Hence, the total pressure force on the curved surface F is equal to integral of rho into g into h into dA. But here, the direction of the forces on the small areas is not in the same direction and varies from point to point. Hence, integration of equation for dF for curved surface is impossible. The problem can, however, be solved by resolving the force dF in two components, such as dFx and dFy in the x and y directions respectively. The total force in the x and y directions, that is, Fx and Fy, are obtained by integrating dFx and dFy. Then, the total force on the curved surface F is equal to the square root of Fx squared plus Fy squared. The inclination of the resultant with the horizontal is tan phi, which is equal to Fy by Fx. Resolving the force dF in the x and y directions, we get dFx is equal to dF into sine theta, which is equal to rho into g into h into dA into sine theta, and dFy is equal to dF into cos theta, which is equal to rho into g into h into dA into cos theta. The total forces in the x and y directions are Fx is equal to integral of dFx, which is equal to integral of rho into g into h into dA into sine theta, which is again equal to rho into g into integral of h into dA into sine theta. Fy is equal to integral of dFy, which is equal to integral of rho into g into h into dA into cos theta, which is again equal to rho into g into integral of h into dA into cos theta. Observe the enlarged area dA or delta EFG in the image. In the image, EF is equal to dA. FG is equal to dA into sine theta, and EG is equal to dA into cos theta. Thus, in the equation, dA into sine theta, which is equal to FG, is again equal to the vertical projection of the area dA. Hence, the expression rho into g integral of h into dA into sine theta represents the total pressure force on the projected area of the curved surface on the vertical plane. Thus, Fx is equal to the total pressure force on the projected area of the curved surface on a vertical plane. Also, dA into cos theta, which is equal to Eg, is equal to the horizontal projection of dA. Hence, h into dA into cos theta is the volume of the liquid contained in the elementary area dA up to free surface of the liquid. Thus, integral of h into dA into cos theta is the total volume contained between the curved surface extended up to the free surface. Hence, rho into g into integral of h into dA into cos theta is the total weight supported by the curved surface. Thus, Fy is equal to rho into g into integral of h into dA into cos theta, where Fy is the weight of liquid supported by the curved surface up to the free surface of liquid. What is buoyancy? We have completed the first topic on total pressure and center of pressure. Let's proceed with the next topic on buoyancy and flotation. A buoyant force is the force applied upward on an object by any fluid. When a body is immersed in a fluid, an upward force is exerted by the fluid on the body. This upward force is equal to the weight of the fluid displaced by the body and is called the force of buoyancy or simply buoyancy. The center of buoyancy is defined as the point through which the force of buoyancy is supposed to act. As the force of buoyancy is a vertical force and is equal to the weight of the fluid displaced by the body, the center of buoyancy will be the center of gravity of the fluid displaced. Well done! You have completed this module and your progress has been recorded. You are most